New solar device makes water, oxygen and fuel from moon soil. Imagine a breakthrough where the very dust of the moon is transformed into water, oxygen and high-energy fuel, all by harnessing sunlight and a little help from astronaut exhalations. Recent research has uncovered a surprisingly simple method to extract these essential resources from lunar regolith, opening up new possibilities for sustaining future colonies on the moon. For years, scientists have known that vast amounts of water are locked within the minerals of the lunar surface. However, most of the earlier ideas for resource extraction involved complex, energy-demanding processes that could prove unsustainable in the long term. This new approach, pioneered by Lu Wang from the Chinese University of Hong Kong and his team, offers an elegant alternative: a solar-powered reactor that uses the combined power of sunlight and the carbon dioxide produced by astronauts to trigger a series of chemical reactions in the soil. In their experiments, the researchers worked with genuine lunar samples brought back by China's Chang'e 5 mission, as well as simulated samples made from terrestrial rocks. The process begins as the sun's light and heat free water from the soil. Then, the lunar regolith itself acts as a catalyst to drive a reaction between the extracted water and CO2. This reaction not only produces carbon monoxide, oxygen and hydrogen, which can be used as fuel, but also leaves behind extra water for other critical uses. One of the key players in this reaction is a mineral called ilmenite, which is believed to significantly enhance the conversion process. Hai-Hui Joy Jiang of the University of Sydney, who was not part of the study, remarked that the chemical reaction is both intriguing and potentially vital for producing essential resources on the lunar surface. He also noted that additional research is needed to determine if this method can be scaled up effectively for practical deployment on the moon. Despite the promise of this technology, scaling it up to meet the resource demands of a lunar colony poses substantial challenges. The extreme conditions on the moon, ranging from drastic temperature fluctuations to an intense solar radiation environment, ultra-high vacuum, and low gravity, create unique obstacles. Additionally, the natural variability of lunar soil and the limited availability of CO2 further complicate the practical implementation of this innovative process. But here's where it gets controversial. Can a system that seems so straightforward really overcome these daunting challenges to support a self-sustaining lunar habitat? Are the potential benefits worth the significant technical hurdles? We invite you to share your thoughts and join the discussion. Do you see this as a viable path for lunar colonization, or a concept that might be too idealistic in the face of real-world obstacles? Moon dirt to water and oxygen, the revolutionary device for lunar bases. Imagine living on the moon, where every sip of water and breath of oxygen is a precious commodity. But what if we could turn the very dust beneath our feet into these life-sustaining resources? This isn't science fiction. It's the groundbreaking focus of a recent study that could revolutionize lunar exploration. Researchers have developed a device that heats moon dirt to extract water, then uses that same water to convert exhaled carbon dioxide into oxygen and fuel. It's a game-changer for long-term lunar bases, where shipping water from Earth is not just expensive but downright unsustainable. Here's the eye-opening reality. Sending water to space costs a staggering $83,000 per gallon, according to NASA. An astronaut consumes about 4 gallons daily, and that's just for drinking, forget hygiene, cooking, or growing plants. Over a 6-month mission, the water needed for one person would fill a small barge. Even with falling launch costs, water remains the heaviest and most costly item to transport. But here's where it gets controversial asterisk. What if we've been overlooking the moon's hidden treasure all along? Lunar soil, or regolith, contains trace amounts of water molecules, locked within its minerals. The challenge? Extracting it requires heating tons of dirt for just a few gallons of water. Yet, the payoff is immense. Water not only sustains life but also provides radiation shielding, and when split becomes rocket fuel. The device in question uses photothermal catalysis, a process that harnesses sunlight to heat a black ceramic reactor to over 1,800 degrees Fahrenheit, vaporizing water molecules from the soil. And this is the part most people miss asterisk. The same heat is then used to convert carbon dioxide into oxygen and fuel, creating a self-sustaining system. Tests using samples from China's Chang'e 5 mission and synthetic substitutes showed promising results, proving the sun's energy is all we need. No electric heaters required. The compact design means a fridge-sized lander could process hundreds of pounds of dirt daily. A key player in this process is ilmenite, a titanium iron oxide found in lunar soil. Not only does it store hydrogen, but its iron atoms also aid in converting CO2. 1 ton of ilmenite-rich regolith can yield up to 168 pounds of drinkable water, enough for 50 people daily. Plus, the leftover metallic iron can be used for construction or radiation shields. But here's the catch: ilmenite deposits are concentrated in specific regions, requiring detailed mapping and heavy machinery to access. And let's not forget the moon's harsh environment. Extreme temperature swings, radiation, and abrasive dust pose significant challenges. Despite these hurdles, progress is undeniable. China's plans for a robotic base by 2035 and NASA's Artemis program for crewed missions highlight the growing momentum. This device could be the missing link to making lunar habitation a reality. But here's the question we can't ignore: are we ready to embrace in situ resource utilization as the future of space exploration? Or will the technical and financial barriers prove too daunting? Let us know your thoughts in the comments. This is a conversation worth having. Scientists extract water and oxygen from moon dust using sunlight. Lunar colonization breakthrough. Imagine a future where we can breathe and fuel our rockets on the moon, all thanks to a simple process using sunlight and moon dust. But is it really that simple? Let's dive into this exciting scientific discovery and explore the possibilities and challenges it presents. A revolutionary idea: water and oxygen from moon dust. Scientists have found a way to extract water and oxygen from the moon's soil, or regolith, using sunlight. This could potentially provide a sustainable source of resources for future lunar settlers. But here's where it gets controversial. Is this method economically viable? A team of Chinese scientists believes so. They've developed a one-step process that integrates water extraction and photothermal carbon dioxide catalysis, potentially enhancing energy efficiency and reducing infrastructure costs. Lu Wang, a chemist from the Chinese University of Hong Kong, expressed their surprise at the success of this integrated approach. However, the team acknowledges that transporting supplies from Earth to the moon is incredibly expensive. Studies suggest it would cost a whopping $83,000 to transport just 1 gallon of water, and astronauts would need to drink 4 gallons per day. So finding an alternative source of water and fuel on the moon itself becomes crucial. The moon, it turns out, has abundant water, but it's not as straightforward as it seems. Water is brought to the moon by various celestial bodies and is trapped in minerals like ilmenite, mainly found in permanently shadowed craters at the lunar poles. Extracting this water for drinking is relatively simple, but the Chinese team has taken it a step further. They've developed a process to produce methane, a potential rocket fuel, by combining extracted water with carbon dioxide and using lunar soil as a catalyst. Philip Metzger, a planetary physicist and co-founder of NASA's Swamp Works, explains the novelty of this approach. He believes that methane, being easier to stabilize than liquid hydrogen, could be a more desirable rocket fuel. Many commercial companies, like China's Landspace, are already utilizing methane-powered rockets. The water-bearing ilmenite also plays a crucial role in producing oxygen and methane. The Chinese team has developed a one-step process to achieve this, first heating the regolith to release the water, and then adding carbon dioxide to catalyze the reaction. While previous technologies could accomplish similar feats, they required more steps, machinery, and a catalyst that would need to be transported from Earth. The Chinese team's process is believed to be more efficient and cost-effective, but Metzger remains cautious. Lunar regolith is an excellent thermal insulator, making it challenging to heat it evenly. This could reduce the amount of water produced in a given time. One solution could be to tumble the regolith, but this adds mechanical complexity and increases the risk of breakdown in the harsh lunar environment. Metzger also highlights a potential issue with carbon dioxide supply. Astronauts may not produce enough carbon dioxide through normal exhalation, and transporting it from Earth would defeat the purpose of the proposed technique. However, he suggests an alternative catalyst, nickel-on-kieselguhr, which could be more efficient and reusable, making it a potentially cost-effective solution in the long run. The research team has successfully demonstrated the feasibility of using lunar regolith as a catalyst. The next step is to scale up the technology and prove its efficiency and sustainability in lunar conditions. This includes accounting for weaker gravity, extreme temperature fluctuations, and intense radiation. Metzger believes there may be additional applications for using lunar soil as a photocatalyst. While he remains skeptical about its economic competitiveness, he acknowledges that good ideas often have detractors, and proof lies in doing the work. While we're not yet ready to build a permanent lunar base, the upcoming NASA Artemis missions provide an excellent opportunity to trial these technologies and determine if we can truly live on the moon. The research, published in the journal Joule, opens up exciting possibilities for the future of space exploration. What do you think? Could this be the key to sustainable living on the moon? Join the discussion and share your thoughts in the comments.